All right, great. So the topic that we're going to learn about today is rotational kinematics. You saw the word kinematics, right? Obviously, when we started learning physics, that was our first unit. But now we're going to be doing kinematics, but in the rotational form. So that's why I said in the beginning of the course that you guys really understand the beginning stuff, because physics is kind of like a building block. You need the stepping stone in the front in order to move forward, kind of like math. How you need algebra 2 in order, you need algebra 1 for geometry, or algebra 2. Same thing with physics. You need the basics in order to build off of what you learn. And this is basically where it comes to. Now we're going to start off with rotational kinematics. It's going to be kind of lengthy with some content, but I'm going to see if I can try to finish this up before 3:50, because if you didn't see my post, right, we have this MIT webinar on how this person got into MIT last year, and he's actually from Francis Lewis. So if you guys are interested, just please join if you want to. I put the Zoom link in Google Classroom, so you don't have to pre-register. But if you're interested, feel free to join. So just going back to rotational kinematics, we're going to start off with day 1, right? The content. And we're going to start off with tangential quantities, tangential speed, tangential acceleration. Then we're going to be talking about rotational motion, angular velocity, angular acceleration, rotational kinematic equations. Then we're going to talk about centripetal force, right? What does it mean for something to have a centripetal force? And obviously forces create acceleration, right? Because of Newton's second law. So we're also going to be talking about what centripetal acceleration is, and hopefully we have time for some practice and for you guys to ask questions if you want to. All right, moving on. So what do you guys think a radian is? Right, you guys heard about degrees, radians. What is the difference between a radian and a degree? If I say this angle has a radian of 2, or like this angle has a degree of 180, what is the relationship? What is a radian? All right, so a radian is basically a unit of angle. It's basically like a degree, except it's a smaller measurement. It's like 1 radian is approximately, I think, 57.7 degrees, because in a circle, right, you have 2 pi, right? A circle has a radian of 2 pi, a full circle, right? And half a circle is pi, and then 90 degrees is pi over 2, right? Because that's basically what radians are. Now, in order to find a radian, you have to use the formula S over R, which is basically the arc length of a circle or whatever arc you have divided by its radius, and that gives you the radians. Sometimes I think on SAT they have this as well, right? They ask you convert degrees into radians, and they give you something like 180. They want you to convert it to radian. Then you multiply it by pi over 180, which is just pi over 1, which is just pi. That's basically what we're going to be talking about with radians today. The reason why radians is important is because it's a unit that we will be using in rotational kinematics. All right, so next, what is the difference? To start off with the question, what is the difference between tangential motion and angular motion? For example, right, what is the difference if I say angular velocity versus tangential velocity? Feel free, just yourself if you have any questions. All right. So basically, tangential motion it deals with linear. Like before, when we started talking about momentum, energy, velocity, speed, that's all straight things, right? We're saying a straight pattern. This object moves forward, backwards, left, or right. It's straight. It doesn't rotate. It doesn't do any of that fancy stuff. It just does a straight motion. That's basically what tangential motion is, except in this scenario, tangential motion is more specific. It's, what do you guys think the word, what word can you find in tangential? All right, I'm hoping you guys said tangent, which is basically if something is tangent to something, it's perpendicular. So if I say, like, if I don't know if you guys say calculus or anything, but in calculus, if you're finding the tangent of a line, it's basically the line that's perpendicular to the curve or that point. Basically, in tangential motion, it's the same thing, except we're dealing with motion that's perpendicular to centripetal force and things like that. Now, we also have this term called angular motion or angular quantities, which includes angular velocity, angular acceleration. And angular is basically, if you can see the word, angle, right? It deals with angles. So if you have angles, you're dealing with rotation because it's a circle. It's a circular motion. So angular motion is, or quantities, is basically dealing with things that rotate. So clockwise, counterclockwise. It doesn't deal with linear and non. It doesn't deal with linear. It deals with rotational. So in this brings us to tangential speed and velocity. If you guys can see the GIF right on the left side, you see this red dot, right, red circle or something blob, and then you have an arrow, right, and that arrow is pointing. It's keep on going in circles, stuff like that, right? But if you could like slow this down and see it as frames per second, your arrow, which is your actually the direction of your tangential velocity or tangential velocity, is perpendicular to the center every time. When it goes up, right, it's the arrow is pointing to the right, but it's always perpendicular to the radius. If you go to the, if you look at the circle on the bottom, right, if you just pause it in your brain at the exact bottom, your tangential velocity is to the left, but it's still perpendicular to your radius. All right, so hopefully you guys kind of understand this. And then you also have the equation v equals 2 pi r over t. The reason why is just because we know that velocity is displacement over time, right? And what is the distance in a circle? What is the displacement or of a circle? It's 2 pi r, right? It's the circumference. So your circumference divided by your time, which some people also call the period, is your velocity. And we call this tangential velocity because it's the velocity of the object moving at that very instant, the instantaneous velocity at one certain point. And that's why we use the word tangential or tangential, which is perpendicular. It's always perpendicular to the radius. The velocity's direction always perpendicular. And it's also a vector, right? Because it's velocity. If it's speed, it's not. If it's velocity, it does take into consideration of direction. And also basically what I said, velocity is tangent or perpendicular to its radial acceleration. Radial acceleration is basically centripetal acceleration, which you guys will see later. All right, so we also talk about tangential acceleration. Tangential acceleration is also usually in the same direction as tangential speed or velocity. The reason why is because when something is moving in a circle, right, it's constantly curving. It's like the velocity vector is always perpendicular to the tangential velocity vector is always perpendicular to the radius or the center, right? At any point, if you could think, right, any point on this circle, the tangential acceleration or the velocity is always perpendicular to the center. But you might be asking, right, this object is going in a circle, but if its tangential velocity is not towards the circle, why is it moving in a circle? Just to clarify, if you guys didn't quite understand what I just said, right? Let's say at this very point, right? This velocity vector is pointing this way. So the object should be moving in this direction, right? But we see that this object is actually moving in a circle. So that doesn't make sense, right? We know that acceleration is change in velocity over time. But acceleration also does take into account of direction because it's a vector as well as velocity. So if your tangential acceleration is in the same direction as your tangential velocity, right, your object should be moving to the left as well, right, with no change in direction. But it's going in a circle. So this basically leads us to our next point, which is also before I move on, we have units per second squared, meters per second squared as a unit for tangential acceleration, right? Just acceleration, but when we're talking about a circle, and it's usually in the same direction as tangential speed and velocity because it's constantly like accelerating. But at every point, if you could think of it at the very instant of time, like 0.00, like if you just pause the entire system in one frame of time, right? That object is actually accelerating forward. But then you'll see as time increases, the velocity vector is kind of shifting, like it's shifting slightly like every second, which is why the object is going in the circle. If it's just straight, right, it would not be going in the circle, because that wouldn't be true. So this leads us to our next point, which is angular velocity. Angular velocity is basically we measure this angular velocity tells us how fast is this object traveling relative to a circle or a degree. And the reason why I asked you in the beginning, right, what is a radian, is because angular velocity is, the unit for angular velocity is radians per second. We don't use degrees per second because usually degrees are kind of large. Like if you have a 720 degree, you don't want to write 720 over per second, right? You would denote that as a radian, right? And that would be what, 4 pi, I think. And that would be much easier. So we use radians per second. And it's basically, a radian is, again, talking about what I said before, is the change in, it's basically the degree measure, but it's in a different unit. It's in a radian, which is a smaller quantity. So it's easier to calculate things like that. It's basically like degrees, but you have to convert it into a radian. All right. And then if you wanted to find a degree or a radian, you would have to do S over R, which is the arc length over the radius. I believe this is in radians. The data is units is in radians. So angular velocity, we use this Greek symbol omega, which is basically the W, which you can see. The W is basically V over R. It's velocity over radius. You might be asking, where do you get this equation from, right? So I'll tell you right now. So we know that tangential speed or tangential velocity is your arc length over your period, right? 2 pi r in that scenario if you're going in a full circle. But if you're not going in a circle, we just denote that as S, right? It's your arc length. So S over T is your tangential velocity, right? It's the distance you travel in an arc divided by your time it takes. But in this scenario, we're using radian. So it's actually a measure of degree. It's not a measure of arc length. The reason why it's different is because, let me just see if I can draw this out. All right, so let's say we have a small circle right here, right? And then we also have a big circle, right? But if we can draw this, if we can put a center, right here, and then right here, and then same thing right here and right here, right? And then arc length, let's see if we draw this degree, it's called theta 1, this degree, theta 2, call this S2, which is the arc length, and S1, right? Your theta, which is your radians or degree, is equal in both scenarios, right? But your arc length is not, because it's a larger radius. So your S1 is actually greater than your S2. So this is why we use angular velocity, because sometimes your circles and stuff will not be the same. But if you could use radians per second, it's uniform. It's the same for both scenarios, because the degree does not take into account of your arc length. So just skip back. Let's start off with a quick derivation. So we know that change in theta right, that equals change in S over R, right? Because theta is S over R. That's how you would calculate an angle, or in radians. It will give you in the answer in radians. Now we know that omega is the rate at which you travel an angle with relation to time, right? It's kind of like, it's like velocity is displacement over time, but omega, or angular velocity, is change in your theta over time. So we could say this equation. Sorry for I apologize for my handwriting. I'm trying to draw with the mouse, which isn't going really well. But right, change in theta over time, that is your omega. And we could also say that that equals 1 over R times your change in arc length over your change in time. Because let's see how I can explain this. Your change in theta is delta S over R, right? We know that. So if you're doing delta S over R and you're dividing that by time, you keep change flip. So you keep your delta S over R and you change the division sign to multiplication sign, and then you multiply it by the reciprocal of time, which is 1 over time, which is why you get this equation. You could either write it this way or you could write it out as this way. You could write it as delta S over R, right? This times the reciprocal of 1 over reciprocal of time, which is this. So if you have delta S, right, if you multiply everything out, it should bring you to this equation. Delta S over R delta T. Right, and we have delta S over R over delta T. Now delta S over delta T is velocity because it's tangential velocity, because we have right, as I said before, velocity deals with arc length, but angular velocity does not. That's why angular velocity could be the same for two different circles, but the two different circles can have different radiuses, which means one could be larger than the other. But the tangential speed would not be the same because tangential speed does take into account of arc length. So in the circle, your tangential speed is your arc length over your time. And same thing, right? If you have linear velocity, it's your displacement over time. But in this scenario, your displacement is your circumference, or the amount of the circle that you travel, which we say as the arc length. So your arc length is denoted as the variable s, right? So if we write this equation, right, rewrite it, we could say that is actually v over r. So you get this equation v over r, which equals omega, or angular velocity, because right, like in math, right, if you have delta s, if you have, let's see if I can find a good math scenario. If you have 3 over 1 times 3, right, so it's 3 over 1 times 3, you have a 3 on the top and a 3 on the bottom, so that cancels out to 1. So then you end up with 1 over 1 because you have the other one that was left on the side. Same thing in here. If you have delta s over r times delta t, your delta s over your delta t is just the variable v, or tangential velocity, right? So if you're left with that, you can factor out 1 over r times v. And 1 over r times v is the same thing as 1 over r times v over 1. So you just cross, I'm not saying cross multiply, but you just multiply across, right? Numerator, numerator, denominator, denominator, and then you get v over r. That's omega. So that's where you get this equation from, right here. All right, so I hope that clears up stuff. Also, you do have to talk about frequency, right? Sometimes problems can deal with frequency. Frequency is just the inverse of period. Period is basically how long does it take you to travel one revolution or across this entire circle once. Frequency is more of every second, how much of this revolution do you travel? That's basically what frequency. So frequency and period are always inverses of each other. Even when we learn about waves later, simple harmonic motion, you'll find out that they are inverses of each other. Frequency is like how fast is this happening every second, and then period is more of like how long does it take to travel one entire revolution. So they're inverses of each other, right? And this is basically where you get omega. So omega could also equal 2 pi f. And you can always play around with equations. You can always make new equations to use depending on the problem. But this is the major one that we use. Omega equals v over r. And omega is w, which is the angular velocity. All right. So we'll move on to next. So we also talk about angular acceleration, right? We have a velocity. We also need an acceleration, right, to describe the velocity. So angular acceleration is basically, right, we have, like, if you think about velocity, right, this is why rotational kinematics is basically kinematics, but in the rotational form, right? If you have an angular acceleration or acceleration, right, that means that you have to have a velocity. If you have a velocity, you need to have acceleration because your velocity could change. And if it changes, how are you going to describe that change? You have to use acceleration, right? Because acceleration is changing velocity over time. Same thing here, right? You have angular velocity, But what if your angular velocity changes, right? What if it increases? What if it starts rotating faster? Then you need to have an acceleration to describe that. And that is basically what we use as angular acceleration. And we use this variable right here, alpha. If you guys took chemistry before or something, you probably do recognize it as like, I think it was a radioactive symbol or something. But this is basically alpha. All right. And we know that acceleration in the linear form is change in velocity over time. But in this scenario, we don't have a regular velocity. We have an angular velocity. And we just said that angular velocity is equal to omega, or the Greek symbol, like looking like a W. So we say that alpha, or angular acceleration, is equal to the change in angular velocity, which is change in omega over time, right? Or it could be over the change of time, because right, your time can change as well. And the same thing right here, right? It's kind of like finding the slope, right? If you have like they give you 2 coordinates on a problem and they ask you to find the slope, you just take the y2 minus y1 over x2 minus over x2 minus x1. Same thing here. It's basically the slope between the w final, omega final minus omega initial over t final minus t initial. Same thing with velocity, same thing with the acceleration. When you look on a graph, this is why graphs are really important in physics, is you will have a like the slope of the velocity is basically your acceleration. The slope of angular velocity is angular acceleration. But right now we're not talking about like calculus yet. But if you guys are interested in learning calculus for physics C, I don't know if you guys are taking it, but you will get deeper, right? The derivative, or basically the slope of something, right? The derivative of speed, the derivative of displacement is velocity. Derivative of velocity is acceleration. Derivative of acceleration is, I think it's like you go into Crack-Snapple, something, like it goes, you have like 6 derivatives, 7 derivatives, it just goes crazy. It's like at one point you don't understand what is going on. It's like, what happens after acceleration? Like it's like very conceptually demanding. But for now, we'll just deal with alpha. Alpha again is angular acceleration, and it's changing omega over time. All right. We also use an equation called v squared over r. All right, this is also equal to omega. You will also need to use this in your future problems. This also equals omega. I'm sorry, alpha. Yeah, v squared over r. I think there is a picture on the next slide with the derivation that shows you it, but right now I don't have the time for it. I will in the future, but just write this down if you're taking notes or something. You will need to use this equation. It's v squared over r. You get this equation from this equation. But it's a complexing derivative, the complexing derivation, and we have to cover everything right now. So we'll skip that for now. All right, next. So we talked about angular acceleration, talked about tangential speed, tangential velocity, tangential acceleration, angular velocity, angular acceleration, and now we have something called rotational kinematics, right? We also talked about kinematics in the beginning, right, with projectiles. You shoot a ball, right, and it goes in the air off a cliff, or with a theta of, or angle of 30 degrees, with a velocity, initial velocity or something, right? They ask you to find the time it takes or the distance it travels, right? We use the kinematics equation. But now we have rotation. So we also have something called rotational kinematics. And we also call these rotational kinematic equations. So the key thing here is, if you know your kinematic equations, you know your rotational kinematic equations. If you don't know your kinematic equations, you won't know your rotational ones, because they come from the same thing. You just change the variables. So I'm just going to write this out also really quick. Annotate. Right. Velocity, this is linear. Let me just type this out, much easier. Linear. And then this is rotation. Right. In linear, we have the variable v, and that's velocity. In rotational, we also have velocity, but we call that omega. and that is equal to angular velocity. Right, and then we also have acceleration in linear, right? If we talk how fast is a car accelerating, we use that, and that is equal to a. We use the variable a. And here we use the symbol alpha, which equals angular acceleration. Right? And then next we have change in displacement, right? Displacement. What is displacement or something? That's delta x. So we use delta x in for displacement. And delta x basically comes from x minus x naught, which is basically what you see in the image right here. It's just more, what do you say? It's not super simplified. It's like a more detailed, or like the original equations. When we say delta x, we're basically saying the same thing, but we just move the x naught to the other side. So it becomes x minus x naught, and that's change in displacement, which is change in your final position minus your initial position, which is displacement. All right, same thing. We use delta theta, and that equals change in radians. Right, it's always radians. We don't use degrees. All right, and then we also have time. Time doesn't change because, right, you can't change time. Time is time. You don't have a separate. I mean, if you go to theoretical physics, you have another dimension, which is like, I think it's light or something. But right now, time doesn't change, right, for our case. So time exists in both scenarios. So this equals time, and it's also seconds. All right. Sorry if the notes are kind of crammed on one side. I tried to keep it as the image as big as I can, so there's not a lot of space. But I hope you guys kind of understand it. On the bottom also tells you, right? And we also use a subscript naught, which is 0 or initial, as the initial acceleration, or the initial angle, or the initial omega, right? What you start off with, what the problem gives you, what you start off with, we use the symbol naught or 0 subscript. If it's final, we use f. Sometimes the problem, some of these equations, they don't subscript it with f because they're assuming that that's the final magnitude, but you should always be clear with what you're assuming. So this in this scenario is your, if it doesn't have a subscript, it's your final. All right, we'll clear this, and hopefully we can move on. All right, so we kind of talked about tangential and angular quantities, and now we're going to do a little comparison. So angular quantities, right, the units is radians and seconds. And then they're all vector quantities, right, because angular quantities deal with positive values and negative values, and that's counterclockwise and clockwise. Clockwise is CW, which is a negative value, and then counterclockwise is CCW, and it's a positive value. This is what we use in physics. Pretty sure if you go to engineering or to stuff like that, in the future, like with torque and stuff, you'll also use the same rules. Tangential quantities, sorry for the typo, but it's basically what we talked about before, like linear stuff, meters and seconds. So we have some scalars, we have some vectors, because you can have tangential speed, which is a scalar, it doesn't take into account of direction. And we also have tangential velocity, which is a vector, because it does take into account of direction. And that direction would be up or down at that very instant. I don't think it would be I don't think it would be clockwise and counterclockwise, because when you're talking about tangential velocity, it's at that very instant. What is the tangential velocity? And if you just look at it at that instant, your arrow is either pointing up, pointing down, pointing south, pointing east, pointing south of north, anything like that. All right, so next. So the last thing we're going to talk about is centripetal force. Centripetal force is basically what allows something to orbit, or if you learn about orbital dynamics, or on something to go in a circle, it's because of centripetal force. Now you might, this is kind of conceptually demanding. I'm just telling you right now, it took me a long time to understand it. You're like asking, like, if this object is not going towards the sun or going towards the center, why does it have a force in that direction, right? You guys might be asking, like, if I'm on a roller coaster, I'm not going down, I'm just going in a curvature. Why is there a centripetal force going downwards? Same thing, right? If I'm running on a track really fast, or I'm running a car really fast, right in the top right scenario, my car is not going towards the center. It's going in a circle, but it's not accelerating towards the center. Why is my force towards the center? And I hope this answers your question. Centripetal force is a force, right? Centripetal force is a force. Now we also need from Newton's second law that every force always creates an acceleration if the mass is constant, right? If your mass is not remain this even regardless of mass, it always has an acceleration. If you're applying a force to something, it always will generate an acceleration. Now, centripetal force is a vector, meaning it takes into account of direction. So if your velocity is going forward, right? Your tangential velocity is going forward at that very instant, which is perpendicular to the center or the centripetal force. Your centripetal force also creates something called centripetal acceleration. So if you could see in this picture as well, right? If you're going in a circle, right, your tangential velocity is always perpendicular to the center, but it's not what do you call it? Like, so centripetal acceleration is change in velocity over time, and because it's a vector, it takes into account of direction. Let's see if we can draw this out real quick. Kind of running out short on time, but let's see if we can finish this today. You have a velocity that's going right. This is a circle. Your velocity is this way, and then you have a centripetal force going this way. Your velocity is going to shift. So at this point, it's going to go this way. At this point, it's going to go this way. And at this point, it's going to go this way. And at this point, it's going to go this way. But why is it shifting? It's because of centripetal force. Because the centripetal force creates an acceleration, which is centripetal acceleration. And acceleration changes velocity. It doesn't change velocity just by magnitude, but also changes its direction. That's why, like on an icy day, if your car has a high acceleration, it's hard to slow it down because it's like you have a force, but it's not like how do you call it? Like you have a force and acceleration, but it's not easy to change it. Same thing if you're like on a track, right? You're running in circles. You're sometimes like this. If you see like from the side view, your track is actually like a triangle, because at this point it's exerting a force this way. Like if you look at it from the side view, like assuming this is your car, and it's got wheels and it's like going in this direction, right? It's like an incline. It's pushing it towards the center, which creates that acceleration. And we also use the equation v squared over r. You guys can look at the slides and also try to see if I can explain this next week. But this is basically it, I believe, for today. Just like take this time, sink it in. And if you don't, we'll stop it here today. I'm also trying to keep my classes kind of short because I know like 1 hour can be kind of long for you guys and you guys have stuff to do. So, if you have any questions, you always let me know. If you don't, you guys can go now.